Welcome to the Deep Dive. This is the show where we take on some of the most monumental topics and really try to deliver the core insights straight to you.
And our mission today is, I think, one of our most ambitious yet.
It really is. We're going to try and unpack the life and work of a man whose influence is so fundamental, so, baked into the modern world that he basically wrote the blueprint for the 21st century.
We are diving deep into John von Neumann, and this is a figure who wasn't just brilliant. I mean, he was revolutionary in, 4 or 5 different fields at the same time?
At the same time, yeah. He pioneered the architecture of the computer you're using right now. He formulated the rigorous math for quantum mechanics.
He invented the entire field of game theory.
And on top of all that, he designed key parts of the atomic and hydrogen bombs.
The scale is just staggering. It really is.
It honestly is hard to internalize. I mean, it almost feels mythological. Take this quote from a Nobel laureate, Hans Bethe. He looked at von Neumann's brain, his mind, and wondered out loud if it was evidence of a species superior to that of man.
I mean, what higher praise can you even get, especially in that era, which was full of geniuses?
Totally.
And it was completely warranted. If you just look at his math output, the sheer breadth of it is shocking. He was foundational in set theory, functional analysis, ergodic theory. I mean, the list goes on. He contributed to almost every part of math that existed then. Almost everything, yeah. The only big exceptions were number theory and topology. And that kind of range, that ability to blend the purest, most abstract ideas with the most urgent practical applications, it's just unparalleled.
Okay, so let's try to unpack this powering figure. We really need to trace his path and understand how one person did all this.
Where do we start?
We'll start with his origins as this unbelievable child prodigy in Budapest. Then we'll get into his work as a pure math revolutionary, fixing the foundations of modern physics.
And then finally, his role as this industrial and defense powerhouse, the man who shaped the future we're all living in today.
Right, to really get the scope of his mind, you have to start with the setting. He was born Neumann János Lajos in Budapest back in 1903.
And this wasn't just any city. This was like the intellectual hothouse of Central Europe.
Absolutely. It was the place that produced that incredible group of geniuses they famously called the Martians.
Right. That included people like Leo Szilard, Edward Teller, Eugene Wigner.
An unbelievable concentration of talent. And von Neumann's family was wealthy and non-observant Jewish. His father, Mixa, was a very successful banker. He even had a doctorate in law.
So he grew up in a family where intellectual achievement was just the norm.
It was the baseline. And that gave him a huge advantage educationally and socially.
And their social status became even more official later on, didn't it?
It did. That's a key detail.
Yeah.
In 1913, for his service to the Austro-Hungarian Empire, John's father was elevated to the Hungarian nobility by the emperor.
And this is where the famous von in his name comes from. Exactly. It granted the family this hereditary title, Margitai, which means of Margita. So in German, the academic language of the time, Neumann János became Johann von Neumann.
And then just John von Neumann when he came to the States.
Right. But, the real origin of his fame was the raw speed and capacity of his mind. We're talking about a true, once-in-a-generation child prodigy.
The stories are they sound made up.
They really do.
Yeah.
Like by the age of 6, he was apparently joking with his father in ancient Greek.
He was 6 years old.
And by age 8, he'd already mastered differential and integral calculus.
So he's doing university-level math before most kids have even gotten to long division.
It's just a different category of mind. And his reading, even as a 12-year-old, was just stunning.
Right. He read that incredibly complex French math text.
La théorie des fonctions by Émile Borel. And this wasn't light reading. This is a book on set theory and measure theory that gives graduate students headaches. He didn't just read it, he absorbed it.
And it wasn't just math, right? He was obsessed with history, too.
Oh, completely. He read this massive 46-volume world history series and could apparently recall huge sections of it verbatim. Dates, battles, political movements. It was all just there.
So his family was clearly fostering all of this talent. They weren't just pushing him into science.
Not at all. They really believed in a broad global knowledge base. He was tutored in English, French, German, and Italian. He was also fluent in Yiddish, Latin, and ancient Greek.
He would relax by reading ancient Greek historians in the original language.
Yeah, and I think that synthesis, the deep historical knowledge combined with that mathematical mind, is what made him such a devastatingly good strategist later in life.
Now, even with all this spectacular talent, His career path wasn't just a straight line into pure mathematics.
No, there was a very practical compromise he had to make early on.
His father, the banker.
Right. His father was worried that being a pure mathematician wasn't, a financially stable career. He actually asked the great aeronautical engineer Theodor von Karman to try and talk his son out of it.
But he found a very von Neumann way to solve the problem. He just did both.
It's the perfect von Neumann solution, isn't it? Optimize for both outcomes at once. So he chose chemical engineering as the practical high-income field.
He went to ETH Zurich for that.
Passed the ridiculously hard entrance exam, graduated in 1926. But, and this is the key part, he did that while also getting his PhD in mathematics from the University of Budapest.
Which he also got in 1926.
Summa cum laude.
So he basically earns a top-tier applied science degree and the highest possible pure math degree in the exact same year.
And that dual focus, the abstract rigor and the industrial application, that really becomes the theme of his entire life.
And right away, his math work showed he was here to, revolutionize things, not just contribute.
Immediately. At just 19, while he's juggling these 2 degrees, he publishes this paper that redefines the concept of ordinal numbers. It actually replaced Georg Cantor's original definition.
So he's not just learning the tools, he's redesigning the plumbing of mathematics itself.
While he's still a teenager.
So, okay, let's talk about his rapid ascent in the academic world after that.
It was just meteoric. Even in the most competitive places in Europe. By 1928, he becomes the youngest person ever elected private dozen at the University of Berlin.
Which is like a lecture position, but unpaid.
Right, but incredibly prestigious. And his output at this time was just staggering. The sources say he was writing almost 1 major mathematics paper per month.
A month. The pace is just.
Yeah.
It's unsustainable for a normal human. And then he makes the move to the United States.
He comes to Princeton in 1929 as a visiting lecturer. He becomes a U.S. citizen in 1937. But the big move was in 1933.
The Institute for Advanced Study.
Exactly. He accepts one of the original 6 professorships at the IAS, right alongside people like Albert Einstein. That really cemented him as a pillar of American science.
And he brought a very different kind of personality to the quiet halls of Princeton. The stories about his work habits are amazing.
He was not the quiet, sequestered academic at all. He was a social animal. He loved parties. He loved entertaining.
He apparently did his best work in noisy, chaotic environments. He found quiet stifling.
Which leads to the famous story about the German march music.
Right.
He would blast this incredibly loud German march music from his home in Princeton while he was working, often late into the night, driving his neighbors crazy.
And yet, all this socializing, it didn't seem to affect his focus at all.
Not in the slightest. There's a story that he could be at a party until 2 in the morning, drinking, chatting, and still give a perfectly brilliant, groundbreaking lecture at 8:30 a.m.
His mind just never seemed to need to reboot. It was just always on, always running.
And that social fluidity, combined with the intellectual rigor, made him incredibly effective in committees and organizational roles.
Which is such a crucial detail for his later defense work. He was known as an amazing chairman.
Unparalleled. He would give in easily on personal stuff, organizational things, which made people like him. But on technical and factual matters, he was completely uncompromising.
Herbert York, who worked with him on defense strategy, said the von Neumann committees were just remarkable in style as well as output.
He was the ultimate translator between abstract science and actionable policy. And that really set the blueprint for how science got integrated into military planning, especially for things like long-range missiles.
He was the perfect intellectual broker. His daughter said he was really concerned with 2 things in life: enjoying it, which he did, and making sure his intellectual contributions would last.
And to make them last, he first had to take on the biggest mathematical crisis of the 20th century.
Okay, so that brings us right into part 2, his revolutionary work in pure math and physics. And this crisis you mentioned, it started because the very foundation of math, set theory, was kind of broken.
It was threatened by paradoxes. The most famous one is Russell's paradox.
The set of all sets that don't contain themselves.
Right. Does that set contain itself? If it does, it doesn't. If it doesn't, it does. It's a logical contradiction that just pulls the rug out from under all of modern math.
It's basically the mathematical version of this sentence is false. It just creates an endless loop.
Exactly. And von Neumann tackled this problem head-on in his doctoral thesis in 1925. And his solutions are now just permanent fixtures of logic and set theory.
So how did he actually solve that self-referential paradox.
He used two really brilliant connected ideas. First, he introduced what's called the axiom of foundation.
Okay.
Think of math as being built in stages, like with blocks. This axiom just says that sets have to be constructed in an ordered way. If set A is an element of set B, then A must have been built before B.
Ah, so you can't have a set belong to itself, because that would mean it had to be constructed before it was constructed.
Which is impossible. It just breaks the loop by enforcing a strict hierarchy. The second idea was the concept of a proper class.
What's that?
He made a formal distinction between a set which can be a member of other classes and a proper class, which is a collection so huge that it cannot be a member of anything else.
I see. So the paradoxical object, the class of all sets that do not belong to themselves, is allowed to exist.
But only as a proper class. And by definition, a proper class can't belong to itself. So it fixes the contradiction by basically changing the object's legal status in the mathematical world.
It's an incredibly elegant fix. But just as he's shoring up the foundations of math, his friend Kurt Gödel comes along and just blows them up.
This is maybe the biggest turning point in von Neumann's entire career. At the time, the big goal was something called Hilbert's program.
To prove that all of arithmetic was absolutely consistent and complete.
Exactly. Using simple, finite logic. Von Neumann was a huge believer in this program. He'd even had some success with it.
And then comes this conference in 1930.
It was seismic. Kurt Gödel gets up and announces his first incompleteness theorem. He proves that any sufficiently complex system, like arithmetic, is inherently incomplete.
Meaning there are true statements within the system that the system itself can't prove.
Exactly. It was a devastating blow to that quest for absolute certainty.
And what's so fascinating is von Neumann's reaction. It was just instantaneous.
Instant. He didn't argue, he didn't doubt it. He immediately saw how profound it was. And less than a month after hearing Gödel speak, von Neumann sends him a letter.
Outlining his own derivation of the second incompleteness theorem.
Yes. That not only are these systems incomplete, they can't even prove their own consistency. You can't use the rules of math to prove that math is sound.
And the fact that he derived this second, even deeper result so quickly on his own just shows his incredible mental agility.
And for von Neumann, this realization was, it was a complete pivot. It drastically changed his views on mathematical rigor.
Because the perfection he'd been searching for was fundamentally unattainable.
Right. So he basically stops doing research into the foundations of math and shifts his focus almost entirely to applications to mathematical physics. If perfection wasn't possible, then utility was the next best thing.
So he moves from the pristine world of set theory to the messy, chaotic new field of quantum mechanics.
Exactly.
Yeah.
And quantum mechanics in the 1920s was a total mess. You had Heisenberg's matrices, Schrödinger's waves. It was all very confusing. Von Neumann took all that confusion and gave it a single, rigorous mathematical language.
And this is where we get the famous Hilbert space.
He was the first person to define an abstract Hilbert space axiomatically. I mean, to put it simply, quantum mechanics needs to handle an infinite number of possible states at once.
Right.
Hilbert space is that infinite dimensional arena. It's the mathematical playground where all the quantum possibilities for a particle get to live.
And his big technical contribution was extending the math to handle what are called unbounded operators.
Yeah, that was key. An operator is like a machine that measures something, like position or momentum.
Yeah.
But some quantities, like energy, can theoretically be infinite. Those are unbounded. He developed the rigorous math to handle those infinite possibilities, which was essential to making quantum mechanics work.
And his 1932 book, Mathematical Foundations of Quantum Mechanics, basically became the Bible for the field.
It codified everything. It basically translated the physics of the quantum world into the pure mathematics of Hilbert spaces and operators. And this clarity led to incredible insights.
Like explaining the uncertainty principle.
He showed that the reason you can't know both a particle's position and its momentum perfectly is because the mathematical operators for position and momentum don't commute.
Meaning the order you measure them in actually changes the outcome.
Exactly. The math itself explained why the physical world was so strange.
But this is where it gets really weird, and he moves from math into philosophy. The measurement problem.
This is his most famous and most controversial analysis. He's trying to figure out why the wave function, which describes all possibilities, suddenly collapses into one single reality when we observe it.
And he traces the whole chain of events.
Rigorously. From the particle to the measuring device to the scientist's eye, all the way into the scientist's brain. And he reasoned that since the entire physical universe is subject to quantum rules, the thing that causes the collapse must be something outside the physical system.
His conclusion.
The consciousness of the experimenter.
He thought consciousness itself was a thing that turned quantum possibility into concrete reality.
Now, most physicists today would favor other explanations, like decoherence. But for decades, von Neumann's idea was taken very, very seriously.
And even beyond that, his work is still foundational for things like quantum computing today.
Absolutely. He introduced the idea of density matrices to describe quantum systems that are mixed up with their environment,
Which leads to von Neumann entropy.
which is a cornerstone concept in quantum information theory. It's how we measure the amount of uncertainty or information in a quantum state.
And finally, he even showed that the quantum world operates on a completely different system of logic.
He and a colleague, Garrett Birkhoff, basically invented the field of quantum logic. They proved that the rules of reasoning that apply in our everyday world, classical logic, just don't work for quantum mechanics.
The classic example being the three-filter photon experiment.
Right. Classically, if A and B together block all light, sticking C in the middle shouldn't change anything. But in the quantum world, it does.
And he showed this means that in quantum logic, the order of operations matters. The distributive law we all learned in school doesn't hold.
He literally discovered that the universe uses a different logic than Aristotle would have recognized. It's just a breathtaking achievement.
So he formalizes the rules for the atom, and then he was on to formalize the rules for human interaction, economics, strategy, game theory.
Yes, this is where he becomes the ultimate strategist. He essentially creates the entire mathematical field of game theory with one paper in 1928 where he proves the minimax theorem.
So for anyone who hasn't encountered game theory, what's the core idea of the minimax theorem?
Well, it applies to what are called zero-sum games with perfect information. So think poker or chess, where one person's gain is the other's loss and everyone knows the rules. The theorem proves that in any game like that, there is always an optimal strategy. A strategy where each player can choose a move that minimizes their maximum possible loss. It guarantees a stable, logical solution exists.
Which is great for chess, but applying that kind of rigid logic to the messy world of human economics, that must have seemed crazy at the time.
It was completely revolutionary. And its influence just exploded with his 1944 book, Theory of Games and Economic Behavior, which he wrote with the economist Oscar Morgenstern.
The reception was huge, right? The New York Times ran a front-page story on it.
It was a sensation. Suddenly people were talking about using poker strategy to solve complex business problems.
And in the book, he basically told economists that the main mathematical tool they were using, calculus, was wrong for the job.
He did. Traditional economics relied on the smooth curves of calculus, but von Neumann argued that real-world economies are full of sharp turns, tipping points, sudden changes, just like in a game.
So he told them they needed to use his kind of math, functional analysis.
Exactly. He said the future of economic theory was in using things like convex sets and topological fixed-point theorems.
Okay, a fixed-point theorem. Can you simplify that for us?
Think of it like a perfectly stable point on a map. A fixed-point theorem proves that if you have a complex system, there has to be at least one point of equilibrium, a point where all the forces balance out, where supply equals demand.
So it guarantees a stable solution exists, even in a really complex system.
Which is something traditional calculus couldn't always do, and his own model of an expanding economy was the perfect demonstration.
He proved that in his model, the economy's growth rate had to be equal to the interest rate.
He did, and that whole methodology, using functional analysis, it became the foundation for the work of future Nobel laureates like John Nash.
Wow.
It's been called the greatest paper in mathematical economics.
So if the minimax theorem brought strategy to economics, his meeting with George Dantzig brought computation. I love this story.
It's a great one. So George Dantzig had just invented linear programming, a way to optimize how you allocate resources.
But he hadn't quite figured out the deep mathematical structure behind it.
So he explains his problem to von Neumann at Princeton, and Dantzig said that von Neumann started getting really impatient while he was talking.
Because he'd already seen the answer.
He'd already solved it. And without any notes, von Neumann just launches into this spontaneous hour-long lecture. He connects Dantzig's problem all the way back to his own work on matrix games from 1928.
And right there on the spot, he basically invents the theory of duality.
He did. Dantzig was just, quote, dumbfounded. Duality is this beautiful idea that every optimization problem has a mirror image. So maximizing your profit is mathematically the exact same thing as minimizing your costs? Von Neumann saw that connection instantly.
And he didn't just stop at the theory. He also figured out better ways to actually solve these problems on computers.
That's the utility-focused mind again. He later developed the first interior point method for linear programming,
Which is a much faster way to find the optimal solution for really big, complex problems.
much more efficient. It was this perfect blend of abstract theory, computational need, and real-world application that just perfectly set the stage for his next and maybe most enduring legacy, the digital age itself.
Yeah, part 4 is where von Neumann really becomes a global architect, and it starts with computing. He got involved as a consultant for the U.S. Army on the ENIAC and EDVAC projects in the mid-40s.
And it's here that the idea that powers literally every computer, tablet, and phone we use today is born, the von Neumann architecture.
It's his most famous legacy, for sure. The idea was laid out in this hugely influential paper he wrote in 1945, the first draft of a report on the EDVAC. And the core concept was the single-memory stored program architecture.
Can you explain why that stored program idea was such a huge leap forward?
Well, before this, computers were programmed from the outside. You had to feed them instructions on paper tape, or even worse, you had to physically rewire the machine to change the calculation.
A huge, tedious process.
Unbelievably so. Von Neumann's idea was to store the program's instructions in the exact same memory as the data it was working on, so the computer could treat its own instructions like any other piece of data.
Exactly. And that meant the computer could modify its own program as it was running. It could make decisions, it could branch. It instantly made the computer a universal, flexible machine.
And while his paper didn't credit all the engineers involved, it provided that essential conceptual blueprint for pretty much every computer that came after.
And he immediately put it into practice, designing the IAS machine at Princeton, which became the basis for the first commercially successful IBM computer.
He wasn't just thinking about the hardware, the architecture. He was also a pioneer of software.
Oh, absolutely. He invented the merge sort algorithm in 1945. It's a super efficient way to sort data, and it's still one of the best general sorting algorithms we have today.
And his name is also tied to another incredibly powerful computational tool from that era, the Monte Carlo method.
Right. He developed this with his friend Stanislaw Ulam. It's a way to use randomness to get approximate answers to problems that are just too complicated to solve directly.
Like the simulations you'd need to design a nuclear bomb.
Exactly. It was a revolutionary way for computers to simulate reality by basically playing dice over and over again statistically.
And he had a pretty funny take on the quality of the random numbers they were using.
He did. He knew they weren't truly random. They were generated by these crude mathematical formulas. He famously said, "Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin."
But he justified the sin because it was useful.
Precisely. His crude method was fast. And more importantly, when it broke in a really obvious way, so you knew something was wrong. For von Neumann, utility and speed often won out over mathematical purity.
And this genius for computation wasn't just limited to physics. He also went into theoretical biology, years before we even knew the structure of DNA.
This is maybe his most predictive work. He and Ulam basically created the field of cellular automata, these simple grid-based models that can produce incredibly complex behavior.
And that led him to think about self-replication.
Yes. He used this model to mathematically analyze what it would take for a machine to build a copy of itself. He designed this elaborate 2D cellular automaton that could do just that.
A universal constructor.
A universal constructor. It's just incredible to think he was modeling the logic of how life replicates before we had any idea about the biological mechanism, DNA.
So now we have to turn to his most impactful and probably his most terrifying work. His role as a defense scientist.
His involvement really started with his expertise in the mathematics of explosions and shaped charges. That made him absolutely essential to the Manhattan Project at Los Alamos.
And his main contribution there was designing the explosive lenses for the implosion-type bomb, Fat Man.
This was the hardest part of the whole project. You had to create a perfectly symmetrical shockwave to crush this plutonium core. A lot of people thought it was impossible, but von Neumann insisted it could be done, and he developed the mathematical models to prove it.
What was the key number he came up with?
His calculations showed that for the implosion to work, the shockwave could not be off by more than 5% from perfect spherical symmetry.
An incredibly tight margin.
And without his mathematical certainty that it was possible, the whole project might have taken a very different path.
His math also dictated how the bomb was actually used to maximize its destructive power.
Right. His calculations on shockwave reflection in 1944 showed that the bomb would be far more destructive if it was detonated a few kilometers above the target, not at ground level.
Because the reflected shockwave would sweep across a much wider area.
And that insight directly informed the strategy used against Japan.
After the war, he immediately became a huge advocate for the next weapon, the hydrogen bomb.
He and Edward Teller were relentless. He even co-filed a secret patent in 1946 with Klaus Fuchs, who we now know was a Soviet spy outlining a design for an H-bomb.
So he really becomes this superstar defense scientist, translating these abstract ideas into hard geopolitical reality.
He did. As a member of the Atomic Energy Commission, he became the #1 advocate for the Intercontinental Ballistic Missile, the ICBM. He personally convinced President Eisenhower to make it the country's highest research and development priority.
And his argument for it was based entirely on the power of the warheads he'd helped create.
Exactly. The early missiles were wildly inaccurate, but von Neumann argued that it didn't matter. If you put an H-bomb on top, the blast radius is so huge that you don't need to be precise. That technical argument completely shaped the Cold War arms race.
Finally, we have to talk about his foresight on global systems, weather, and even climate change.
He realized that modeling these complex global systems would require immense computational power, so he founded the Meteorological Project at the IAS in 1946. By 1950, they were running the world's first numerical weather forecasts on the ENIAC computer.
So the same machine designed for atomic blasts was now predicting the weather. And his observations about the climate were just chillingly prescient.
In a 1955 article, he looked at industrial carbon dioxide emissions and wrote that they may have changed the atmosphere's composition sufficiently to account for a general warming of the world by about 1 degree Fahrenheit.
This is decades before climate change was a mainstream concern.
Decades! And he even proposed early ideas for geoengineering, like spreading dark material on the polar ice caps to absorb more heat. But he was also extremely cautious.
He warned that climate control could be weaponized.
He warned it could pose a greater risk to global stability than ICBMs because the side effects would be unpredictable and potentially irreversible.
And tying all of this together, computing, war, climate, he identified this looming challenge that we are still dealing with today.
He did. He's credited with the first use of the term technological singularity. He saw this ever-accelerating progress of technology and realized it was on a collision course with our traditional geographical and political units, a conflict he called the maturing crisis of technology.
Okay, let's spend some time on the legendary personality behind this intellect. The stories about his mental speed and memory are just central to who he was.
His memory was just famous. It was often described as photographic, especially for symbolic information. There's a story that someone tested him by asking how A Tale of Two Cities begins, and without even pausing, von Neumann just recited the entire first chapter verbatim and only stopped when they asked him to.
I've also heard he could memorize the phone book.
That's the story. He would entertain people at parties by having them pick a page at random, and he'd recite the names, addresses, and numbers on that page.
It's just an incredible feat.
Although his close friend Stanisai Ulam believed his memory was primarily auditory, not visual, that he remembered things better if he heard them.
But it wasn't just his memory, it was his processing speed. That's what seemed to set him apart, even from other geniuses.
This is the really humbling part. Enrico Fermi, another top physicist of the time, just flat out said, "Johnny can do calculations in his head 10 times as fast as I can, and I can do them 10 times as fast as you can. So you can see how impressive Johnny is."
The gap was just that huge. And his own professor, George Polya, said he was literally afraid of him.
Polya said that if he ever mentioned an unsolved problem in a lecture, chances were von Neumann would come up to him at the end with the complete solution scribbled on a piece of paper.
Imagine trying to teach someone like that.
Another collaborator, Israel Halperin, said that trying to keep up with his train of thought was like riding a tricycle chasing a racing car.
Which brings us to probably the most famous story about his problem solving. The fly puzzle.
Ah, yes, the fly puzzle. It's the perfect illustration of how his mind worked.
Can you set it up for us?
Sure. So you have two bicycles, they start 20 miles apart, and they're riding toward each other at 10 miles per hour. A fly starts on the handlebars of one bike and flies back and forth between the two bikes at 15 miles per hour until the bikes meet in the middle. The question is, how far did the fly travel?
Right. And for most people, the trap is to try and calculate the distance of each individual leg of the fly's journey.
Which requires you to sum an infinite geometric series. It's a complicated calculation. The simple trick is to realize the bikes will travel for exactly 1 hour before they meet.
So you just multiply the fly's speed, 15 miles per hour, by that 1 hour. So the fly travels 15 miles.
Exactly. So the story goes that when this puzzle was posed to von Neumann, he gave the answer 15 miles, almost instantly.
And the person who asked him just assumed he'd seen the simple trick.
Right. But von Neumann's reply was, "What trick? All I did was sum the geometric series."
So his raw calculation speed was actually faster than the time it would take a normal person to even think of a shortcut.
His brain just went straight for the hard way and solved it before most of us could even formulate the easy way.
Ulam said that most mathematicians really master 1 or 2 tricks, but von Neumann had mastered 3 totally different ways of thinking.
Symbolic manipulation, an intuition for logical structure, and an intuition for the combinatorial superstructure of new theories.
Jean Dieudonné called him the last great mathematician who was equally comfortable in both pure and applied math.
But even with that unbelievable range, there were limits. He didn't really work in some major areas like number theory or algebraic topology.
Which kind of proves his own sad observation later in life, right?
That the field of mathematics was just becoming too vast for any one person to grasp it all.
What's so interesting to me, though, is that even a mind that was so clearly superior still had these moments of deep self-doubt.
Giancarlo Rota wrote about this, that von Neumann had deep-seated and recurring self-doubts, especially about his own creativity compared to someone like Gödel.
He felt like he was just a very fast processor, but not a true creator of new ideas.
He felt Gödel's proofs came from a place of, irrationality or pure creativity that he just didn't have access to. He worried his work wouldn't last.
And his final days, when he was sick, really reveal that struggle.
He was diagnosed with cancer in 1955, and it was possibly from his radiation exposure at Los Alamos. As he was facing death, he converted to Catholicism and asked for the last rites.
His daughter said he was terrified that his life's work would just be forgotten.
But even then, in that final moment, his logic was still running.
Pascal's wager.
He reportedly said something like, "So long as there is the possibility of eternal damnation for non-believers, it is more logical to be a believer at the end."
He was trying to find the optimal strategy, even for the afterlife.
A logical genius applying pure rationality to the ultimate unknown.
But whatever his own doubts were, the consensus among his peers was just absolute.
Claude Shannon, the father of information theory, said it plainly. Von Neumann was the smartest person I've ever met. Paul Samuelson, the economist, just said, he was the incomparable Johnny von Neumann.
I think Hans Bethe's quote really says it all. A brain that suggested a species superior to man. He was just this quintessential polymath whose combined influence on everything makes him one of the true giants of the 20th century. So if we just try to recap the sheer breadth of what this one person did, it's just incredible. He gave us the stable foundation for modern math with his work on set theory.
He gave us the rigorous language for quantum mechanics with Hilbert space.
He invented game theory, which completely changed how we think about strategy in economics, in war, in everything.
He designed the core architecture for every computer we use.
And he developed the key engineering for the atomic bomb and the ICBM.
His legacy is, it's really the foundation of the modern technological state we live in. He was the node connecting pure abstract thought to the most urgent practical needs.
And as we move deeper into this era of technological acceleration with AI and climate instability, his most chilling warning is probably his most relevant one.
That's right. He warned that the technology that was being developed in his time was in conflict with traditional geographical and political units and concepts. He called it the maturing crisis of technology.
Just think about that. He saw the potential for a technological singularity decades before anyone else was talking about it.
And he was the one who warned, back in 1956, that weather control, a technology he helped pioneer, might pose a greater threat to the world than nuclear weapons.
So for your final takeaway, we want you to consider this. John von Neumann, the architect of our world, identified the central challenge of our time, this clash between fast-moving tech and slow-moving politics. Now, 70 years later, how well have our political and global structures actually adapted to the frontiers that he opened up?
And is that maturing crisis of technology he identified still the central defining challenge of our era?
Something to think about until our next deep dive.
Thanks for joining us.
We'll see you next time.
Welcome to The Debate. Today we are diving into the Well, the colossal intellectual legacy of John von Neumann. He's a figure whose sheer scope, it spans pure mathematics, quantum theory, computing, and even Cold War defense strategy. It makes isolating his single most significant contribution a really profound intellectual challenge.
Indeed. When you look at the source material, what just stands out as von Neumann's almost unparalleled ability to translate these incredibly abstract intellectual concepts into tangible, world-changing results. He really operated on that cusp of theory and application, like no one else in the 20th century.
Absolutely. And I think the tension we have to confront is whether the lasting intellectual weight of his legacy rests on the foundations he built for mathematics and physics, or on the structures he subsequently erected in technology and in governance.
Precisely. So the central question for us today is this. Was John von Neumann's most enduring and significant contribution his foundational work in theoretical mathematics and physics, or was it his pivotal, world-changing efforts in applied science and defense technology?
I'm going to argue that his theoretical and foundational mathematical frameworks in set theory, functional analysis, and quantum mechanics, that these represent his most profound and architecturally enduring contribution. These were really the necessary axioms upon which all of the subsequent applications were built.
And I'll be maintaining that his transformative impact lies primarily in his direct, intentional application of those mathematical ideas to solve real-world problems, in defense, computing, economics, things that fundamentally reshaped modern civilization and global power structures.
So to me, von Neumann's genius resided first and foremost in constructing these rigorous theoretical structures, the things that provided coherence to entire fields. He began intellectually by addressing the crisis in set theory that was caused by paradoxes like Russell's, his 1925 doctoral thesis. It achieved a feat of axiomatization, establishing the modern rigorous basis for set theory.
Okay, that work it's certainly a testament to his rigor. I won't deny that. But maybe for a listener who isn't a mathematician, why should they care about something like set theory axioms?
Well, because without that rigor, the entire edifice of modern mathematics, it just collapses into contradiction. He introduced the axiom of foundation and the powerful notion of a proper class. Proper classes are collections that are simply too vast to be considered sets themselves, like the collection of all sets. By defining these, he created this elegant, non-circular hierarchy for sets, resolving the deep contradictions that had, frankly, paralyzed mathematics at the turn of the century. That provided the logical certainty for every mathematician who followed.
I acknowledge the foundational strength of that achievement, I do, but I see that as merely the prerequisite for what came next. To me, his significance is better measured by how those fundamental ideas were immediately applied to reshape 20th century physics, economics, and technology.
Before we jump straight to applications, though, we have to acknowledge his role in formalizing quantum theory. His 1932 work, Mathematical Foundations of Quantum Mechanics, it didn't just explain the physics. It created the rigorous mathematical language we needed to understand reality at the subatomic level. He established the Dirac-von Neumann axioms, unifying the previously competing formulations of Heisenberg and Schrödinger by basing them on the mathematics of Hilbert space and linear operators.
And what does that mean in plain terms?
It means he reduced the uncertainty and the probability inherent in quantum mechanics into a precise, systematic framework. Hilbert space allowed physicists to describe the possible states of a system as vectors, and linear operators allowed them to precisely calculate observables like position or momentum. As Arthur Reitman noted, this was perhaps the most important axiomization of a physical theory to date, and it fulfilled a major part of Hilbert's agenda. This profound theoretical achievement is the prerequisite for all subsequent quantum technology.
I agree that establishing the language is crucial, but establishing the language for the physical world is, well, it's still a theoretical step. My argument is that his enduring contribution is measured by the direct influence he exerted on global affairs and civilization through technology and policy.
Such as?
Okay, let's start with computing. Von Neumann was the pioneer who codified the stored program architecture. This concept, described in his first draft of a report on the EDVAC, it states that a computer should store its data and its program instructions in the same address space. Before this, computers were mainly rewired for every new problem. By making the program essentially just another piece of data, he created the basis of all modern digital computer designs, the architecture that every device listening to this broadcast uses. And then he followed that up by designing the IAS machine, the critical precursor to commercially successful mainframes.
That is a staggering technological transformation, no doubt.
It gets more decisive. His applied efforts directly altered military and geopolitical capability. During the Manhattan Project, he was instrumental in developing the mathematical models for the explosive lenses required for the implosion-type nuclear weapon, Fat Man. This was not abstract research. This was complex, nonlinear fluid dynamics calculated by hand and then implemented with devastating effect. He applied his mind to solving the most urgent existential engineering problem of the war.
And that influence certainly continued post-war.
Yes. Post-war, he was considered the nation's foremost expert on nuclear weaponry, becoming a commissioner of the Atomic Energy Commission. Critically, his chairmanship of the ICBM's Scientific Advisory Committee directly shaped all Air Force long-range missile programs. The source material shows his recommendations ensured the ICBM program was designated the highest priority above all others. This fundamentally defined the arms race and global strategic balance for half a century.
And we can't forget economics, where he founded game theory with the Minimax theorem back in 1928, and later co-authored Theory of Games and Economic Behavior.
Exactly. He revolutionized economics by proving that in zero-sum, two-person games, there exists a unique solution, the Minimax equilibrium. This shifted economics from a purely descriptive social science to a mathematically rigorous predictive discipline. On top of that, his model of an expanding economy used complex fixed-point theorems and inequalities, raising the mathematical level of economics far, far beyond anything previously seen. These are immediate, decisive transformations of the external world, powered by his applied genius.
You build a strong case for impact, but I think focusing solely on the immediate real-world influence, it overlooks the deeper motivation and context for his shifts. Let's consider his intellectual trajectory. He ceased research in the foundations of mathematics only after Gödel's Stickkind incompleteness theorem demonstrated that foundational work had reached an inherent self-imposed limit.
Meaning what exactly?
Meaning that von Neumann, who valued mathematical rigor above all else, pivoted to areas where definitive answers and clear mathematical structures were still possible. This was a theoretical decision, you see, guided by the limits of logic, not just a sudden vocational shift toward engineering. He focused on areas like ergodic theory or, profoundly, lattice theory, where he introduced continuous geometry.
Continuous geometry? That sounds abstract even by his standards.
Oh, it is deeply abstract, but it shows his continued pursuit of pure structure. In continuous geometry, the dimension of subspaces isn't restricted to integers, 1D, 2D, 3D, but can range continuously across the unit interval, from 0 to 1. This concept arose directly from his abstract work on von Neumann algebras, the theory of operator algebras he founded. This profound extension of geometry, driven by the internal necessity of pure analysis and algebra, has no immediate obvious technological application. It is a masterpiece of pure thought.
That's a fascinating theoretical curiosity, sure. But I would argue his shift after Gödel demonstrated his ultimate ambition was tied to solving tractable, high-impact problems. After that foundational roadblock, he, quote, instead spent time on problems connected with applications. This movement wasn't merely a philosophical retreat. It led directly to techniques that solved massive physical crises.
Can you elaborate on that connection?
Well, it led directly to the development of the Monte Carlo method, for instance. Faced with these complex hydrodynamic and nuclear simulations where analytic, precise methods failed because of the sheer number of interacting variables, he pioneered approximation via statistical sampling. This was a pragmatic solution to a massive engineering and physics bottleneck. Likewise, his work in fluid dynamics resulted in the classic solution to blast waves, the Taylor-von Neumann Sedov solution. This provided a crucial mathematical framework for understanding shockwave propagation, directly informing the design and safety of both conventional and nuclear defense systems. He moved to applications because that is where his mathematics could yield the most decisive, immediate result.
I'm not convinced that the Monte Carlo method, a tool for approximation, outweighs the definitive axiomatization of set theory. But let's pivot back to computing, as that is where our two positions intersect most visibly. You insist the architecture is the core of the computer revolution.
Look, I come at it from a different way. The blueprint defines the house, right? The stored program concept in the EDVAC report wasn't just an idea. It was a workable, implementable design for physical hardware that became the basis of most modern digital computer designs. He made computations systematic, sequential, and scalable. Without that architectural insight, which is an applied engineering feat, all the theoretical math in the world would have just remained confined to specialized analog machines.
I'm sorry, but I just don't buy that the architecture is his core contribution, even in computing. Let me tell you why. While the architectural influence is undeniable, his theoretical contributions to computing often came first, and they dealt with complexity and logic in a far, far deeper sense. Consider his work on self-reproducing automata.
You mean his theoretical designs for self-replicating machines?
Exactly. His elaborate 2D cellular automaton was a deeply conceptual, abstract analysis of self-replication. It used complex rules and states within a cellular grid to demonstrate mathematically how a machine could be a universal constructor, capable of reproducing itself and constructing any other specified automaton. This abstract, foundational logic of self-replication was published before the structure of DNA was even discovered. His work on complexity, on cellular automata, and the theory of reliable organization from unreliable components, these are profound mathematical insights into life and computation that are, to me, far more enduring than the specific tube and wire design of the IAS machine.
That's a compelling argument about conceptual foresight, that he anticipated the logic of life. But let's look at the conceptual implications of his quantum work again. You noted the framework was rigorous, but what about the actual meaning he derived from it?
That is one of his most lasting theoretical contributions, the measurement problem. In his 1932 text, he confronted the discontinuity introduced by observation. He concluded that the collapse of the wave function, that moment a quantum system transitions from a probabilistic cloud of possibilities to a single observed reality, could not be accounted for by the physics itself. He mathematically proved that if the observer's consciousness must be the cause of the collapse. This intellectual framework challenges our fundamental notion of reality and remains an active, unsettled philosophical debate rooted entirely in his foundational mathematics. It is an intellectual distress that will last as long as physics does.
I respect the depth of that philosophical challenge. I really do. But it is exactly his technological and strategic deployment that defined the political and military reality of the 20th century. He didn't just pose questions, he provided the answers that shaped the modern world. His advisory influence in the defense sector was almost unprecedented. His word was essentially gospel inside the White House and the Pentagon on matters of nuclear strategy.
The political applications are clear, but I prioritize the theoretical depth.
Well, consider his late work on global applications, which demonstrates a mind focused on solving the ultimate planetary-scale challenges facing the human species using applied intellect. We discussed his climate foresight. His 1955 paper, Can We Survive Technology?, presciently observed that the burning of fossil fuels, quote, may have changed the atmosphere's composition sufficiently for global warming to begin.
That's stunning foresight, admittedly.
It is more than foresight, it is an applied mandate. Following that observation, he spent his last years developing models for climate prediction, resulting in the world's first numerical weather forecasts performed on the ENIAC computer, and subsequently proposed radical, direct interventions like spreading colorants on ice caps to modify the global energy balance. This is applied genius leveraged to address global survival, a focus that transcends mere pure mathematics.
I would maintain that those applications, however transformative or prescient, were only possible because he first created the stable, fundamental language. His theoretical insights, his axiomatizations in set theory, the creation of functional analysis, which provides the tools for modeling complex systems, the framework for game theory, these remain the non-negotiable bedrock for every subsequent generation of mathematicians, physicists, and computer scientists. The foundation endures, even if the structure built upon it changes.
And I maintain that the measure of his colossal intellect is not how deep he dug the foundation, but the sheer size and decisiveness of the cathedral he built upon it. His most visible and decisive legacy is the application of his intellect to immediate large-scale problems, from the implosion device and ICBM design to the permanent architecture of the digital computer. He changed not just how we think about the world, but how we live, fight, and calculate within it.
It is perhaps his unique ability to integrate these two spheres, the pursuit of pure mathematical certainty and the pragmatic application of that certainty, that led colleagues to call him the most influential mathematician who ever lived.
The source material makes it clear that the depth of the legacy of John von Neumann warrants continued rigorous examination. Whether you prioritize the abstract language he created or the physical reality he shaped, his work continues to define our intellectual and technological landscape.